Thank you for coming, everybody, to our workshop on intermolecular forces. Dr. Neely has already begun. We'll go ahead and jump into it from here. As she was speaking, she was talking about gases, liquids, and solids. Um, and Go ahead, I'll let you can continue from there. And
Okay, thank you, Professor DePaul. So, yeah, just to brief you, it's going to be repetition, but to brief you on if you arrived a little bit later, intermolecular forces are attractive forces between atoms or molecules, and in general, they are much weaker than ionic and covalent bonds. And just so that you can get a concept of why and what and how, I'm going to describe the three states of matter, and we're going to talk about the relationship of the kinetic energy of the particles, either atoms or molecules, in relation to the interactive the intermolecular attractive forces. So in the gaseous phase, the question is, would you expect the kinetic energy of the particles to be less than, equal to, or greater than the intermolecular attractive forces that holds molecules together? And just to give you a tip, remember we said that the intermolecular attractive forces exist in condensed states. So somebody answered. Can somebody tell me what is the relationship between the kinetic energy of the particles in relation to the intermolecular attractive forces? Is it
absolutely, Victoria, you're right. It's greater than the forces. And the truth is, any substance can be in a gas, liquid, or solid state, even substances that have very strong intermolecular forces, or substances that have very weak intermolecular forces. It can be in a gas, liquid, or solid state, or even a plasma state, which is the fourth phase of matter. Well, there's actually a couple more, but anyway, the the thing about it is that intermolecular forces become more and more important in condensed phases of matter. Unfortunately, in less condensed phases of matter, like gases, the particles are moving so quickly that the intermolecular forces are not strong enough to really make a significant difference. So, like for example, even water molecules in the gaseous state, water has very powerful intermolecular forces, but in the gaseous state, they're moving so fast they can't stick to one another. Think about it like, for example, if you had a very powerful magnetic bullet, okay, and you fired that bullet past a metal building, even if it was within a few inches of the metal building, it would be moving so fast that it would not be able to be attracted to the building enough to cause it to hit the building or stick to the building. However, if you simply pulled that metal bullet out and you walked it past the metal building, you pulled that magnetic bullet and you walked it past the metal building, it would probably fly. It would fly right out of your hand and it would stick to the metal building because you're moving so slow and because you're close to the building. It also depends on how strong the magnet is. The stronger the magnet, the more likely it is to, the stronger the attraction, the more likely it is, even in a higher temperature, a higher kinetic energy state, to stay together in a condensed phase. So it's kind of like a delicate balance. The stronger the attractive forces, the higher the temperature that's needed, the more kinetic energy is needed to separate them into a gaseous phase. But the weaker the intermolecular forces, the lower energy, lower kinetic energy, the lower the temperature must be for those intermolecular forces to be strong enough and significant enough to get them to stick together.
Yes, exactly. So the bottom line is that if we consider, for simplicity, if we just consider the three states of matter as being gases, liquids, and solids, in the gaseous state, the kinetic energy of the particles is much larger than the intermolecular attractive forces, whereas in the condensed state, the liquid state, the kinetic energy is on par, it's about equal to the intermolecular attractive force. And in the condensed state of the solid phase, the kinetic energy is much, much less than the intermolecular attractive force. It's a very basic concept. It's rather important for the understanding, of the, what leads to these states of matter. And so we have described it in as simple terms as possible, and we hope that you can kind of keep it in the back of your head while we really get into the intermolecular attractive forces. So your book describes 3 to 4. I'm going to say 4. I don't know which copy you're using, but in general, we can describe 4 intermolecular attractive forces. And why do I keep referring to these intermolecular forces as attractive? Any ideas, any guesses, any feedback? So the reason we describe them as intermolecular attractive forces is because they are all electrostatic attractions. They're all electrostatic attractions in the liquid or solid state. And what type of electrostatic attractions are they? Well, this is where we get into the concept of a dipole. And this figure, and thank you, Professor DePaul, this figure is very descriptive. If you have an atom or molecule that are polarized, it means that part of the particle is positive, and you'll see in this cartoon below that the partially positive, the positive side of the particle is denoted by the Greek term delta with the plus. Delta plus, and it's in pink. It distinctly and conspicuously shows that the particle is polarized. Part of the molecule is partially positive, and the other part of the particle is partially negative, denoted with the Greek letter delta and a negative sign. So when you have a particle, an atom or a molecule that is polarized, it's going to have a dipole associated with it. And the type of intermolecular force that a substance has essentially is going to be based on the type and the strength of the dipole. Next slide.
And you can just think of dipole meaning 2 poles, 2 sides, one positive, one negative.
2 sides, one positive, one negative, and kind of keep that, keep that in your head, because that's going to come up again when we talk about polarizability. And you have heard about the term polar in social terms. For example, if a person is bipolar, it means that they can have extreme happiness and extreme depression in a less controlled way. And here we're talking about two poles, bipolar, or the scientific term when you have a polarizable molecule is that they have a dipole moment. Now, we can start to introduce the three and really four. In a few minutes, we're going to show you a video where Professor Dave talks about 4 types of intermolecular attractive forces, and textbooks can't make up their minds if they're going to describe 3 main intermolecular attractive forces or 4 of them. But the concept, once you get the concept, it doesn't matter. So we're going to start with the weakest type of intermolecular attractive forces, and it's a good time here to introduce the Professor Dave.
Professor Dave here. Let's talk about intermolecular forces. He knows a lot about the science stuff.
Can everybody see this screen, and can everybody hear Professor Dave?
I can.
Yes, it's a yes. Yes.
Yes,
So I'm going. Okay, thank you.
Professor Dave explains. What is happening when a liquid boils? Why do different liquids boil at different temperatures? To answer these questions, we have to learn about intermolecular forces. These are the electrostatic interactions between molecules. So atoms within a molecule make covalent and ionic bonds with each other, but molecules also participate in interactions with other molecules. Let's look at the different types. First, we have ion-ion interactions. Large ionic solids are held together by these networks of ionic bonds, which are the strongest intermolecular force because they involve formal charges. After that, we have ion-dipole interactions. So first, we must understand what a dipole is. The covalent bonds in a water molecule are polar because oxygen is more electronegative than hydrogen and will pull the electrons in the bond towards itself. Because of the bent shape of the molecule, when we combine these vectors, we see water has an overall dipole, or a side of the molecule with some electron excess and a side with electron deficiency. Dipoles can make electrostatic interactions because the partially negative side is attracted to positive charges and the partially positive side is attracted to negative charges. So when sodium chloride dissolves in water, the sodium ions make ion-dipole interactions with the negative side of water's dipole, and the chloride ions make ion-dipole interactions with the positive side of water's dipole. Each ion can make several of these interactions, which store a lot of energy, which is why sodium chloride will dissociate in water in the first place. Next, we have dipole-dipole interactions. As you can guess, this is when dipoles interact with each other, as with pure water. When in liquid form, water molecules will move in such a way so as to always be making electrostatic interactions between the negative end of one dipole and the positive end of another dipole. In this case, these dipole-dipole interactions qualify for a special title, hydrogen bonds. This is when dipoles generated by NH, OH, or FH bonds interact with each other. These are just especially strong dipole-dipole interactions. They are especially strong because these are the most electronegative elements, so they will create the most strongly polarized bonds, resulting in a very strong dipole and therefore very strong dipole-dipole interactions. We can almost think of partial charges as some fraction of a formal charge. So the greater the partial charge, the stronger the interaction, though never quite as strong as interactions between formally charged particles. Lastly, we have the van der Waals, or the London dispersion force. These names refer to the same force and are completely interchangeable, so I will arbitrarily refer to them as van der Waals forces. This is the consolation prize of the intermolecular forces because any substance can do it. Only ions make ion-ion interactions, and only covalent molecules with a dipole can make dipole-dipole interactions, but absolutely anything can do van der Waals. For example, take a look at helium. Helium is a noble gas, and due to a full valence shell, it does not make bonds with other atoms. So a sample of helium is just a bunch of helium atoms. Well, the electron cloud around a helium atom will at any time be slightly lopsided or skewed towards one direction. This will result in something called a momentary dipole. This means one side of the atom is ever so slightly partially negative, and the other side is slightly partially positive. This is much weaker than a formal dipole, but it still exists and can be measured. If a momentary dipole approaches another atom, it can generate an induced dipole, meaning the slight partial negativity repels this electron density over to the other side of the atom, so it will also have a slight dipole. And then there can be a momentary dipole-induced dipole interaction, that is the van der Waals force. This is a weak and fleeting attraction, but this is all that monoatomic species and non-polar covalent compounds can do. And for very large molecules like some hydrocarbons, the force can become significant. So the ion-ion force is strongest because it involves interactions between formally charged particles. Ion-dipole is next because it involves a formal charge and a partial charge. Then dipole-dipole, which is between partial charges, and van der Waals, which is between tiny induced dipoles. To see how intermolecular forces dictate phase change, let's do a thought experiment. First, recall that a solid's particles are rigidly packed and not moving. A liquid's particles are moving, but they are still close together and interacting. Gaseous particles are moving and they are far away from each other, so compared to liquids, they basically don't interact. So let's pretend we have three substances: helium, water, and sodium chloride. We will place them at 0 Kelvin, or absolute zero, which is the lowest temperature possible, a complete absence of heat energy, where there is no energy available for motion. Here, everything, even helium, is a solid. In order to go from the solid to the liquid to the gas phase, heat energy has to go into the sample and overwhelm the intermolecular forces that are occurring. In a liquid, there is some energy stored in electrostatic interactions, and whatever amount that is precisely the amount of heat energy that has to be provided to liberate the molecules into the gas phase where they are not interacting and not storing energy, because nature will not tend to go to a higher energy spontaneously. So the energy stored in these interactions has to be provided in some other way. This means that the stronger the forces between the molecules, the more heat energy we will have to provide to melt and boil the sample. So let's take our three substances, slowly raise the temperature, and see what happens. Helium, as it is only participating in incredibly weak van der Waals forces, needs only a minuscule amount of heat energy to disrupt these weak interactions. That's why helium will melt and boil at barely 1 degree above absolute zero. Water, on the other hand, is participating in strong dipole-dipole interactions called hydrogen bonds. There is a significant amount of energy stored in these interactions, so we will need considerable heat energy to overcome them. Water melts and boils at 273 and 373 Kelvin, respectively. Lastly, sodium chloride is making extremely strong ion-ion interactions, so it will take a huge amount of energy to melt and boil this solid. It melts at 1074 Kelvin, which means there's a lot of energy stored in the ion-ion forces. We can use this information to decide which of a given set of compounds might have the highest boiling point. When we ask this question, we are really asking which compound is generating the strongest intermolecular forces. The stronger they are, the more heat energy we will need to pull the molecules apart and put them in the gas phase, so they will boil at higher temperatures. We need to be able to look at a molecule and decide what kind of interactions it will make. If it is a covalent compound with non-polar bonds, it can only do van der Waals. If it is a covalent compound with polar bonds, then we must look at the geometry to see if there is an overall dipole. For example, water has a dipole, but carbon dioxide does not, because even though carbon-oxygen bonds are polar, the direction of these polar bonds causes them to cancel each other out, and the molecule is nonpolar overall. Similarly, compare BF3 with NH3. Again, the molecular geometry determines that this is nonpolar, because the vectors precisely cancel each other out. But with ammonia, all the bonds point somewhat towards one direction, so ammonia has a dipole. CF4 is nonpolar, again because of geometry, but CH3F has just one polar bond, so that has a dipole. If a molecule has a dipole, it can do dipole-dipole interactions. And lastly, formally charged ions participate in ion-ion interactions. See which compounds can do what, and you will be in business. Let's check comprehension.
So yeah, basically that's the essential idea. 3 different types of intermolecular forces. The induced dipoles caused by the random movement of electrons, that would be bond dispersion forces. Then there's the permanent dipoles of polar molecules. They always have a partial positive and partial negative on the two sides of their molecules, and those are attracted to one another. And then lastly, the hydrogen bonding. That's basically anything with a hydrogen, oxygen, a nitrogen, oxygen, or fluorine bond to hydrogen. So HF, HO, or HN. You could actually see in this case between HF and HI, is HF a polar molecule? Or what's the strongest type of intermolecular force present in HF?
If you don't mind me answering, no, I believe it would be hydrogen bonding.
Absolutely, that would be hydrogen bonding. What's the strongest type of intermolecular force present in HI?
Well, in this case, it would have to be dipole-dipole.
Yeah, it would be dipole-dipole. Now, if you don't have a table of electronegativities, you may not be able to say for certain it's dipole-dipole, because for it to be polar, there has to be a significant difference in electronegativity. But generally speaking, if the answers, or rather, if the atoms are not the same, in other words, if it's a different atom or a different, if it's not the same atom, it's not two oxygens or two fluorines, if it's a hydrogen and then a fluorine, then that would be a that would be a polar molecule. There are some exceptions, but generally speaking, if the atom's not the same, it tends to be polar. So yeah, in this case, they're both polar, but HF is one of those special hydrogen bonding molecules because it has HF or HO or HN bond. So I like to jokingly say that hydrogen bonding is fun, spelled F-O-N. HF, HO, or HN. That's hydrogen bonding. If it has any one of those bonds in the molecule, then it'll have hydrogen bonding. Thanks. So HF is going to be hydrogen bonding. HI, that doesn't have hydrogen bonding, but it does have dipole-dipole forces. So which one of those has the stronger of the intermolecular forces? Which one has stronger intermolecular forces? HF or HI?
I would say HF.
Yep. And because it has stronger intermolecular forces, does it have a higher boiling point or a lower boiling point?
I would say higher.
Higher, exactly. Stronger intermolecular forces means it is harder to separate, meaning it needs more energy, and therefore a higher boiling point. Very good. The next one, it's O2 and CH3Cl. So what's the strongest intermolecular force present in O2?
I would, sorry, I was just trying to like clear up something within the chat.
Oh, no
For
problem.
O2, for O2, I believe it would be nonpolar covalent bond.
Exactly, that's nonpolar covalent. So the strongest intermolecular force would be what type?
I would say, van der Waals or the
Van der
Lorentz
Waals, or you could
dispersion
just call it
force.
dispersion forces.
Yeah,
Dispersion
dispersion
forces,
force.
yeah. And then what about the CH3Cl? Is that a polar molecule or a nonpolar molecule?
Definitely a polar molecule.
Hmm. Whenever the central atom, and this is actually a quick reference, a check on whether or not a molecule is polar or not, but whenever the central atom is bonded to different outer atoms, it's going to be polar. If it's bonded to the same outer atoms, then you kind of have to check and see if there's any lone pairs in the central atom. But if it's bonded to different outer atoms, then it's going to be polar. So carbon in this case is the central atom, the first atom listed. The first atom of the compound is usually the central atom. That is bonded to hydrogen, but it's also bonded to chlorine, two different outer atoms. So that's going to make it polar. And it would be polar even if it was CH2Cl2. It doesn't matter if there are even numbers of different atoms because the shape of CH3Cl or CH2Cl2, the shape is such that the more electronegative atoms will always be on one side, and the less electronegative atoms will always be on the other side. So therefore, it will be a polar molecule. And so, yeah, and therefore the strongest intermolecular force it has is what?
Dipole force.
Dipole. So between these two, the O2 and the CH3Cl, which one has the higher boiling point?
I would say NaCl or sodium chloride.
Yeah. Oh, I meant the CH3Cl. Yeah, the CH3Cl has the
Oh,
higher boiling point.
sorry. Sorry.
No, it's okay. That's good. That's good. Okay, so now we go to the next one. And you are correct. NaCl does have a higher boiling point than water. Even though water is what? Water has what type of intermolecular force?
Hydrogen bonding.
Hydrogen bonding. But sodium chloride has ionic bonding. And so really there's 5 different types of interparticle interactions. And forgive me, Professor Neely, I'm going to go ahead and pull up the whiteboard real quickly. 5 different types of intermolecular interactions. So there's there's the dispersion forces, which we already talked about. Interparticle interactions. So there's 5 different types. There's dispersion forces. And actually, I don't know what I'm doing writing when I can actually type. The dispersion forces and everything has dispersion forces. And then there's dipole forces. And that is only polar molecules have dipole forces. Then there's hydrogen bonding. And then there is the interaction between ionic compounds and polar protic molecular compounds. And that is ion-dipole forces. So I'll give you an example of that. But then there's ion-ion forces. These are the 5 different types of forces. Now this one, the ion-ion forces are so strong that they reach the level of a bond, so to speak. Okay? These guys, the dispersion, dipole, and hydrogen bonding, they don't reach the level of a bond. They're not strong enough. They're generally speaking just classified as intermolecular forces. Although if you take biology class you will see that sometimes biology textbooks classify hydrogen bonding as the weakest of bonds, but chemists, generally speaking, don't classify hydrogen bonding as a bond. Well, what about this weird ion-dipole thing? It's a particle interaction, but it's a little hazy. We don't really, there's a disagreement over whether or not they should be classified as uh, bond interactions or whether or not it should be an intermolecular force. Generally speaking, it's put under the umbrella of intermolecular forces, but there are those who disagree and want to try to pull it under the window of bond. So generally speaking, it falls more likely under the intermolecular forces. Probably not a bond, but there is debate in the scientific community on that. So what is ion-dipole forces? He may have mentioned it, but this is like when, for example, you have a water molecule where the electrons on the oxygen of this highly polarized bond are interacting with, like, say, for example, a positive ion like sodium. And because this is a pure positive charge ion, and since it's a very strong partial negative, the attraction between these two is very significant. It's much more significant than even hydrogen bonding interactions. So that's what I would say as far as like
Yeah. Professor DePaul, while we're on this, could you please show us the vector sign showing that the water molecule has a net dipole?
Sure. So oxygen, of course, is a bent molecule. It has two lone pairs, and essentially the the vector dipole would be like there's a strong dipole moment because oxygen is very electronegative and hydrogen is very not electronegative. It's not very electronegative at all. And so there is going to be a significant movement of electrons or flow of electrons towards the oxygen. And that's going to give oxygen a very large partial negative. Not quite a full negative charge, but a very large partial negative charge. And it's going to give the hydrogens on this side a pretty high partial positive charge.
Yes, thank you. This is very good.
No problem. So any questions on that? Any questions on any of these 5 interparticle interactions? Okay, cool. Well, let's go ahead and continue. We'll get to the fun stuff.
Okay, so I will try to go back to the PowerPoint. Let me figure out how to do that. Hold on.
Actually, I can pull it up if you like.
Oh, thank you so much. That would really help.
Okay, let me go ahead and do that.
Thank you so much.
Download. All right. Let's do this. Share. And bam. So.
Yes. Yes, thank you. Okay, so like Professor DePaul explained, these dispersion forces, they are everywhere. And the concept is simple. And what we'd like you to understand is that what happens between atoms or molecules is that at a certain distance next to each other, one of them will induce polarizability on the other one. So in other words, when atoms or molecules approach each other, for a moment, at a certain moment, one of them becomes polar, and it induces polarizability. It induces a dipole, a temporary dipole on the other particle, and thus the electrostatic interaction, and thus the dispersion forces.
And Professor Dave kind of like explained this pretty well in terms of that. Essentially, these are created either by electrons randomly being closer to one side than the other, and that'll cause it to have a random dipole, or it could be close. And one of those that had a random dipole because of the movement of electrons may actually get too close to another electron. Furthermore, these atoms can crash into each other, and that can cause a disturbance. So, but the real idea that we want to communicate here that wasn't explained in the video completely is that these van der Waals forces or London dispersion forces, or just dispersion forces for short, increase with increased number of electrons on the molecule, in other words, increased size, and they increase with the molecule being longer. So if you think about it, a ball is not likely to get tangled up in another ball, right? But if you have a long rope, ropes will tend to get tangled up in each other, even without, like, if you just have a bunch of like Christmas lights strung together, you know, or like sitting together, they'll tend to get tangled up in each other, even if they're not trying to. So longer molecules will have greater dispersion forces, and larger molecules will have greater dispersion forces.
And
Because,
again, to
yeah,
confirm what Professor DePaul says, in general, London forces increase with increasing molecular size. That's number one. And in general, longer molecules will have stronger dispersion forces than compact ones.
mhm. So an example of this is crude oil. It's actually separated based and it's refined based on differences in London dispersion forces. The heavier it is, the more carbons, the higher the temperature that's needed to get it to boil. So crude oil is basically put into this fractional distillation machine, and essentially the ones that vaporize most quickly are driven all the way up, and that would be like methane to butane, and so that's where you get the liquefied petroleum gas like propane tanks and things like that. And then of course for the heavier stuff, uh, as you go down, it takes more a higher temperature, so they come off the column later. So like gasoline would not come off until 120 degrees, whereas the lighter gases would come off at only 20 degrees Celsius. So this is an example of how differences in London dispersion forces can actually be used to separate different substances. So let's take a look at a practice problem. So it says determine which of the following molecules in each pair has the stronger London dispersion forces. So what do you think for part A, which has stronger London dispersion forces? Carbon tetrachloride or CH4?
Just a quick refurbisher before you answer this problem. Remember two principles with the London dispersion forces. One is that in general, the London forces increase with increasing molecular size. And two, longer molecules have a stronger dispersion force than the compact ones. So let's look at example A. Which one is going to have a stronger dispersion force, the carbon tetrachloride or methane?
What do y'all think? I know you got this.
Yay.
Very good.
So, yeah, Professor Depar, can you see the chat while you're presenting?
No, I cannot.
Okay, so Jeffrey answered correctly that it's carbon tetrachloride.
Yep, and because it's heavier. Very good. What about what about the next one? B, H2TE, or hydrogen telluride, or hydrogen sulfide? H2TE or H2S? Which one has a greater London dispersion force?
Okay, so Victoria answered as hydrogen telluride,
Very
which,
good.
yay.
Ironically enough, if you actually look at these two molecules, you'll actually see that both hydrogen telluride and hydrogen sulfide are actually polar molecules. So they also have dipole-dipole forces.
Yes.
And interestingly enough, the, the dipole is stronger for the hydrogen sulfide. So that actually has a greater dipole moment. However, because hydrogen telluride has greater polarizability, the increase in dispersion forces for H2TE actually makes its overall this has stronger intermolecular forces, even though its dipole-dipole forces are weaker. They both have dipole-dipole forces, but the dipole-dipole forces of uh, hydrogen telluride are weaker than hydrogen sulfide. However, the stronger dispersion forces, and I'll just put DISP, more than overcomes its weaker dipole-dipole force.
Because in these molecules, tellurium is more polarizable than sulfur.
Exactly. So when we say dispersion forces are the weakest type of intermolecular force, while that's true per instance, in larger molecules, dispersion forces can actually be very significant. And since these have similar, not the same, but similar dipole-dipole forces, because the dispersion forces of hydrogen telluride are so much greater than hydrogen sulfide, it actually makes this one have a much higher boiling point than hydrogen sulfide. All right, let's go to the last one. Which one of these has greater intermolecular forces? You'll notice in this case that each compound has the exact same number of carbons and hydrogens. Which one has the greater intermolecular forces? Or are they equal?
So Victoria has answered pentane.
Very good.
Yay.
But even if they're exactly the same molecular weight, same number of atoms of each type, longer, unbranched carbon chains are going to have stronger intermolecular force, stronger dispersion forces than branched ones. Very good.
Excellent.
If you don't mind me like adding like just like a little comments like for the dispersion forces, it's just that for me the main indicator that like I was taught like in my class was to mostly focus on the like molar mass. However, though another good feature as you guys also like mentioned as shown in part C is to just look at the is it just look for like longer, more organized
Yes.
structure.
Exactly.
Yes.
Yeah. Molar
So just
mass
a
or
greater surface
larger.
area.
Because a larger molar mass almost always corresponds with more electrons. More electrons means more polarizable. Okay? There's more electrons, then they can be distorted. The cloud can be pushed around in more different ways. So absolutely, larger molecules are more polarizable because they have more electrons, and larger molar
Yes.
mass means it's going to have more electrons.
I apologize if I like spoke like out of turn, and also
Oh,
for
no,
like
no,
a
please feel free to interrupt us at any point. And this session is really for you guys. It's not for us. I mean, we could, you know, you don't need to necessarily sit through another lecture. We really want this to be a more active session with y'all asking your questions and getting uh, answers for those questions, precisely the types of questions that you want to get answers to. And if what we're going over is either, you know, boring you because you already know it, or not what you're really wanting help with, please let us know. We can skip to what you do need help with. Just feel free to just let us know. And these are fluid sessions.
I understand.
Yes.
Um, and also for like a future reference, I tend to stutter, so again, I apologize for like if I sound like my mic is cutting off. It's not. It's probably mostly me.
No, you're totally fine. We haven't really. I haven't noticed an issue. I think I think you're doing fine.
That's amazing. Thank you.
You're welcome.
Yes, thank you. Thank you for interrupting, you know, Victoria and Jeffrey. Also, I know you don't have access to the mic, but we are monitoring the chat. So if anything comes up with you, you know, please feel free. And yeah, again, like Professor DePaul said, that you know, we like these workshops to be, you know, it's for you. It should be a little bit different from your lectures because you know, you get to tell us, you know, what you want. So please speak out of place or in place, you know, or you know, however you know, you like to, you know, we like you to be involved. What is your conceptual understanding of the dipole-dipole intermolecular attractive force?
Oh, so for me, in terms of like dipole forces, this is my personal understanding. The dipole forces are like the basic level in terms of strength force that all polar molecules, regardless of their like species, show. One of the like quickest ways to where I was able to figure out or at least determine a polar molecule is through the Lewis structure of the respective of the of the respective molecule and 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 the resulting overall net dipole moment from from the types of bonds formed between each molecule that makes sorry formed between each atom that makes up each bond within such molecule.
I think you
Hmm.
have the concept, and I'm just going to try to simplify it a little bit. So essentially, you know, what you talked about is how do you predict if a molecule is polar, yeah? So you start with a Lewis structure, you draw the Lewis structure, and then you predict the Vesper geometry. And once you have the Vesper geometry, then you can say, are the bond dipoles symmetrically oriented such that they cancel? And if the answer is yes, then they are nonpolar. And then if the answer is no, then they are polar.
And practically speaking, um, I mean, practically speaking, that can be actually distilled down into if the atoms bonded to the central atom are all the same and there's no lone pairs, it's nonpolar. If the atoms bonded to the central atom are not the same, it's all nearly always polar. And if there's one lone pair bonded to the central atom, it's pretty much always polar. And if there's two or more lone pairs, if those two or more lone pairs are on geometrically opposite positions, then it's going to be nonpolar. But if they're in non-geometrically opposite positions, which is most of the time, it's going to be polar. Those are kind of some simple rules. If you don't want to try to do the vector sum addition uh, thing in your head, or try to think about three-dimensional molecules, that can be helpful. But um, yeah,
Yes. Actually, Professor Depard, really you put it in the most facile fashion. Thank you.
So here's a really interesting little diagram on hydrogen bonding. Um, you'll notice that when it comes to the molecules down here, CH4, SiH4, GeH4, and SNH4, each one of these is nonpolar. Each one of these bottom ones is nonpolar. And as you go to the right, basically down the column, below carbon is silicon, below silicon is germanium. As you go down the column, you'll see that each one of these hydrides is actually a nonpolar molecule. And so each one of these hydrides ends up having dispersion forces as the only intermolecular force. And the dispersion forces do increase significantly as you increase the size. But if you for comparable size molecules that are polar, you see the polar ones always win out. So there's H2Te, it's polar and it's heavy. H2Se, it's polar and it's heavier. And H2S, it's polar and it's heavier. So you can kind of compare these. These are actually similar. This H2Se and GeH4 are actually very similar in terms of their weight. I think they actually might have almost the same weight. But because the H2Se is polar, that gives it this much difference. This much difference. And as far as like boiling point.
And sorry to interrupt you, but the delta that you're describing, the difference is specifically in the boiling point temperature.
Exactly. The change in the boiling point temperature. But one thing that's really interesting is notice that according to the dispersion forces, this should all be going downhill. But something very interesting happens when you have HF, HO, or HN bonds. You get this massive spike upwards because the hydrogen bonding interaction is more than simply a strong dipole-dipole force. The interaction between those lone pairs of electrons on the highly electronegative atom and the hydrogen actually interact in such a way that it almost forms a bond. And it's almost to the level of a bond. And because of that, because of the strength of that, it causes a massive increase in, say, like, for example, the difference between, say, CH4 and water is a dramatic difference than, say, between SiH4 and H2S. So, nor ordinarily what you'd probably expect is for the hydrogen bonding to be right about here. You expect the H2O to be right there if it was just a matter of being a strong polar dipole-dipole force. But that hydrogen bonding is actually something else entirely. It's something unique beyond the simple strong dipole-dipole interaction.
So Victoria or Jeffrey, what does this profile, what does this boiling point profile specifically show us?
It shows that we're going to have to use a lot of thermal energy to overcome the forces between each water molecule.
Yes,
Yeah.
that's right. In a phase transition, and especially when you have hydrogen bonding involved in the case of water, then this input of energy is humongous. Correct.
Another interesting point that you can see from this chart is if you're looking at this from a comparison standpoint, you see that dispersion forces, even though they're the weakest of the forces, notice that with enough increase in weight, dispersion forces can be greater than dipole-dipole forces. Dispersion forces can be greater than dipole-dipole forces because dispersion forces are proportionate to the weight. However,
And why is that? Why is it that that we are seeing that the dispersion forces have overcome, even though, we say that the dispersion forces are everywhere and in general they are weak, but here we see that the dispersion forces have overcome the dipole interaction, the dipole intermolecular. And why is that?
You asking me or are you asking the students?
Yeah, preferably the students, and then if not the students, if not Victoria or Jeffrey, then Professor DePaul.
And it's okay to say you don't know, because this is actually a complicated question.
Well, for me, I feel like it's because for SNH4, comparing it to the polar mass of H2S, we're dealing with like a smaller amount of like hydrogen atoms within this case. So there's like less mass compared like to the like total amount in H2S compared to SNH4. And then let's see. I must apologize, but my mind's kind of blank after that.
No, it's okay. Basically, what it comes down to is that when you have such a large molecule, such a large atom like tin, there's so many electrons that when they're crashing into each other. Keep in mind, these little molecules are moving at hundreds of miles. Well, in a gaseous state, they're moving like at hundreds of miles per hour. And as far as the
Wow.
electrons, they're moving at 1/100th the speed of light, roughly. So these things are whipping around really fast. And at any given moment, when you have so many electrons that are smashing around um, such a large atom, they're going to tend to be unevenly distributed. And so even though the temporary, quote unquote, dispersion force dipole, the temporary dipole in tin is strictly speaking temporary, because there's so many electrons, you get almost a constant effect of these dispersion forces. Plus, furthermore, the heavier a molecule is, the more slowly it moves as a gas,
Yes.
because gases move at the same comparable temperature. They have comparable kinetic energy at the same temperature. So, because they have the same kinetic energy at the same temperature, if it's a heavier molecule, it moves more slowly. So it's a combination of the fact that it does have increased dispersion forces, but it's also moving more slowly. So
Yes.
it's that random motion. The more electrons, the more random motion, the more uh, the greater the size and the duration of those dispersion forces the induced dipoles are going to be. So that's really what it comes down to. And
Thank
it's
you.
just a really good point to kind of keep in mind. But as far as you're concerned, for your class, you're probably just going to be sticking for the most part to comparing apples to apples. So like, for example, you might be asked to compare H2S to SiH4. So like these two guys, they have similar masses, but one has dipole-dipole, one has dispersion. So it'd be easy to understand which one has greater intermolecular forces. But you would not be asked to compare something like H2S and SH4 that have vastly different molar masses, and one has, and the only difference is like dipole-dipole versus dispersion. So you would not be asked to compare something like that, but you would be asked to compare apples to apples, similar size molecules.
And so the only things that you need to remember again is that when you're comparing apple to apple, remember that in general the London forces increase with increasing molecular size. And Victoria, you have mentioned that a few times. Thank you. And also that with the longer molecules, they're going to have stronger dispersion forces compared to the compact ones.
So just to emphasize again, hydrogen bonding can only occur between HF, HO, and HN bonds. Hydrogen bonding is fun.
That's a good acronym.
And then, so uh, this is actually kind of what hydrogen bonding looks like in terms of ice, like in a snowflake. You actually see Whoops. This is in the, so these are the hydrogen bonds, like here, here. I'm like making them in green, I think. I'm colorblind, so I don't know. Yeah, it's just like a repeating pattern of all these little molecules. And like these interactions are really strong, so it kind of helps hold them together. It actually helps hold ice together in this structure that is less dense than liquid water, which is one of the reasons why it floats.
I have a really quick 1-minute video on this. It's a very cute cartoon. Is anybody interested in watching that? Okay, here we go. Yay, thank you. Here we go. So this, I just have to, oops. Can everybody see it? See and hear?
Here, I'll close mine. You still have to do it.
Oops.
Share your entire screen.
Okay, so were you able to see it and were you able to see it and listen to it?
Nope.
Oh, okay.
I
Let me
was
try
still
again.
presenting. Try it again. Yeah, share your entire screen.
Share screen. Okay. Okay. Well, here we go. Share screen. Share screen. That share application screen. That share audio. Share. Okay, and here it is. Let me maximize it.
Float on water to take a sun bath.
Can everybody see and listen to this now?
We're good.
Okay.
No, it is because of density. Density is the measure of mass present per unit volume. Lesser the density, lighter is the object. Now, every water molecule has 2 hydrogen atoms bonded to 1 oxygen atom. However, besides being attached to its own oxygen atom, a hydrogen atom is also attracted to oxygen atoms of other water molecules, forming a hydrogen bond. In liquid state, the hydrogen bonds are not strong. They constantly break and reform. Thus, the molecules get arranged in disordered patterns which leave very less empty spaces. However, when temperature drops below 4 degrees Celsius and ice begins to form, the hydrogen bonds become strong and stable, forming hexagonal patterns which have a large number of empty spaces. These large empty spaces make ice less dense or lighter than water, causing ice to float on water.
It's actually very important because if ice did not float on water, then the oceans would never melt. They would actually be frozen.
Sorry.
No, that's okay. The oceans would be frozen on the bottom and never thaw. It would never thaw. Only the surface would thaw, and only to a depth of a few meters. You would have almost permanent frozen oceans and lakes, and sea life would die off for the most part as we know it. So yeah, we're very lucky ice floats on water.
Yes.
So I'm going to go ahead and share my screen again. Whoop. Bam. Okay, hydrogen bonding, very important. Holds our DNA together, enables us to replicate DNA. These are the hydrogen bonding interactions, adenine and thymine, and cytosine and guanine. So you got our hydrogen bonding. There are 2 hydrogen bonding interactions for the AT interaction, and 3 hydrogen bonding interactions for the CG interaction. Very important. So ion-dipole forces, another IMF. Bum, bum, bum. And like I said, this strongest type of intermolecular interactions occurs when ionic compound is dissolved in a polar compound, usually one with hydrogen bonding, like water. And you can see how this works. The partially positive of the hydrogens is attached to the negative of the chlorine, and the partially negative of the oxygen is attached to the partial positive of the chlorine, or the full positive of the sodium. These do actually have a partial covalent nature. They're almost like a full bond. So that's why I said it's debated as to whether or not they should be called IMFs or whether or not they should be called bonds. Scientists are still debating this. And this goes back to that diagram that I drew for you in the whiteboard. So what are the 5 different types of interactions? And notice that van der Waals forces actually refers not just to dispersion forces, but it actually refers to all of London dispersion, dipole-dipole, and hydrogen bonding. But once you hit ion-dipole and ionic bonding, then it crosses the border. It crosses into something completely different. So are ions involved? If yes, then you just have to figure out if there are both molecules and ions, or if it's just ions. If it's just ions, it's ionic bonding. If it's molecules and ions, it's ion-dipole forces. And then, of course, if you're trying to figure out if it has London dispersion, dipole-dipole, or hydrogen bonding, are polar molecules involved? If there are no polar molecules, it is dispersion. If there are polar molecules, then it definitely has dipole-dipole forces, but it may also be hydrogen bonding. You have to check and see if there's hydrogen bonded to nitrogen, oxygen, or fluorine. If so, you have hydrogen bonding. And if it has hydrogen bonding, it of course also has dipole-dipole forces and dispersion forces. And if it has dipole-dipole forces, it of course also has dispersion forces, because everything has dispersion forces. Clear as mud? All right. No. So, difficult question of polarity. And this is just, we've already kind of gone over this, but basically, yeah, for a 2-atom molecule, if the atoms are not the same, the molecule is polar. If the atoms are the same, it's nonpolar. It's very easy to see with something like HF. For more than 2 atom molecules, you have to use those rules that we talked about already. So I'll kind of skip this because we already seem to kind of know about that. So this is some, like when we're looking at polar molecules, obviously something like this is just a 2-atom molecule, so it's super easy. They're not the same atom, so it's polar. CCl4, this is a 3-dimensional vector picture of it. You can see that the vector is in all opposite directions. The central atom is bonded to all the same outer atoms, and therefore it's nonpolar. NH3, because it's bent down like that, because there's a lone pair of electrons up here, the net flow of electrons is towards the nitrogen, which is up on one side of the molecule. And that's going to cause this to be polar. Of course, the fact that it has NH bonds means it's already polar. It's automatically hydrogen bonding. And then we have the CH3Cl, which we already looked at, and our esteemed, I forget, I'm sorry, is it Victoria? I can't see the chat.
Yes, sorry.
Victoria, yeah, Victoria had already indicated that's polar, and this is why. You can actually see here. And technically speaking, there is a slight dipole moment pointing towards the carbon. If they don't have the same electronegativity, you do get a slight dipole moment. These are not perfectly non-polar bonds. But it's such a small dipole moment, we usually don't pay attention to it. But you can see the net flow of electrons is towards that chlorine. So this definitely has a partial negative up here, and it's definitely a partial positive down here. So like I said, that general rule really helps, that if you have different atoms bonded to the central atom, polar, always. If you have the same atoms bonded to the central atom, then it's usually nonpolar unless we have lone pairs involved, like we do with this guy. BF3, boron, has no lone pairs because it has an exception to the octet rule, only likes to have 3 bonds. These dipole moments are in opposite directions, therefore it is nonpolar. Cool.
Is everybody quite clear on determining polarity? It's actually the rule that Professor Depar gave in terms of you're just going to look at the molecule. If the central atom is connected to similar atoms, then it's nonpolar. If there's a lone pair of electrons, it is polar. If there is more than one lone pair of electrons, unless it's symmetrically sitting above and below a plane with similar atoms, they're all polar. So, you're not going to be expected to, go through drawing a Lewis structure and predicting Vesper geometry and,
Actually, you might. I have to confess, they might actually be expected to do that. I know professors who do. But
Okay.
for example, there's very few cases in which you'll have lone pairs in the central atom and it be nonpolar. What I've just drawn you is one of those examples. XEF3. It's trigonal bipyramidal electron domain geometry. In other words, there's 5 domains around it, but 3 of those domains are lone pairs. And lone pairs tend to occupy what's known as the equatorial plane, the horizontal plane. If you have 3 lone pairs, they're in opposite directions, and therefore the effect cancels out, and you end up with a nonpolar molecule because it's basically linear. Another one that's common is you may have something like this. You may have an XEF4. This is This is another common one that they like to throw at students, XEF4. And this has 6 total electron domains around it, and you have 2 lone pairs, one above, one below. And because this is a square planar molecule, the dipole moments point towards the fluorine, but they cancel out because they're in opposite. This is actually a 90-degree angle between each one of these fluorines. Even here, it's 90-degree angle, square planar. So those dipole moments cancel each other out. And both of these molecules, XEF4 and XEF2 rather, are nonpolar. Both of these molecules are nonpolar because the lone pairs are in geometrically opposite positions. Does that help?
And if you need a refresher, a very good place to go back to is there should be a table in your book with the Vesper geometry. It'll tell you number of electron pairs and then the electron pair geometry, molecular geometry, and examples. I mean, it's probably coming back to you, but if it's not, you know where to go, right? Okay, cool.
So I'm going to skip the carbon dioxide polar because we already kind of went over that. Carbon tetrafluoride, water, we already know that. We already went over that. So if you do have to go through all the steps, you figure out what the formula is for a molecule. For example, PCl3. Draw the Lewis structure. Phosphorus found 3 chlorines. You count the number of valence electrons. Draw a skeleton structure. In this case, PCl3 is 5 valence electrons from the phosphorus, 3 times 7, or 21 from the chlorines. That gives you a total of 26. Subtract the number of electrons you used in the bonds of the skeleton structure, 2 electrons per bond. So we've already used 6 electrons. So that's going to go down to 20 electrons remaining. Place the remaining electrons in pairs on atoms that do not already have a full octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, we placed all of our electrons, and now we can see, okay, so all the atoms bonded to the central atom are the same, but There's a lone pair in the central atom. So is this polar or nonpolar?
Yay.
Exactly, it's polar. Very good. So um, I'm going to skip ahead real briefly. Um, be careful because sometimes even molecules that have like oxygen, ozone, to actually draw that, it actually looks like this. Sometimes even molecules with all the same atoms may actually be polar. In this case, this is because of
Bent
the
geometry, yes.
exactly the bent geometry. Even though it's not so much that they have a dipole moment in each of the bonds per se, but the concentrate the formal charge and the electron, lone pair of electrons in the central atom here give this more negative. Well, actually, strictly speaking, uh, the formal charge is actually negative on these guys because these have actually, this is formally positive because, um, and that's just due to the resonance effects. Um, but once again, you can predict this even just by recognizing the central atom has a lone pair of electrons, and therefore it's going to be polar. Um, the one with only dispersion forces ends up being this guy, which we already talked about a bit. Actually, this one also has only dispersion forces. This one's polar.
Ammonia, other than dispersion forces, what does ammonia have?
Um, Hydrogen bonding.
Yep, very
Perfect.
good.
And ethylene, CH2CO2, ethylene, other than dispersion forces, what does it have?
Dipole forces.
Perfect,
Dipole,
thanks.
dipole. Very good. And then, of course, ozone has dipole, dipole. Um, as far as organic compounds are concerned, you may see organic compounds given. And generally speaking, polarity can be tricky because organic compounds have polar sides and non-polar sides sometimes. But essentially, you can think of polarity tends to increase in organic compounds with an increased number of carbon-oxygen or carbon-nitrogen bonds. The more carbon-oxygen bonds and the more carbon-nitrogen bonds, the more polar the molecule tends to be. Um, and polarity decreases with with an increasing number of CH bonds. So if you have a longer carbon chain, lots and lots of these guys, like if there's 17 of these in a row, then yeah, that's going to be pretty non-polar. And I wanted to touch upon one more thing, and I don't know if we're going to have time. We've got the like dissolves like, etc. And this is just kind of a summary of the intermolecular forces. Um, Blended dispersion forces present in all atoms and molecules, dipole-dipole forces just in polar, hydrogen bonding these guys, and ion-dipole just with an ionic compound is dissolved in a polar product solvent, like water or alcohol. And this PowerPoint is available for you to download off our website. Um, I'll probably share that. I'll share that out with y'all. Um, I want to skip. Well, okay. I think we're going to run out of time. We're not going to really be able to get into the properties affected by intermolecular forces. But one thing I will. I'm going to stop sharing this. But one thing I want to share with you real quick before we leave is where you can find some more information on our website. If you Google TCCSE Science, it'll come up to our website. And under Chemistry Web Resources, you go down to Chemistry 1412. In addition to the video tutorial library, which is basically a video textbook. It goes over everything you need to know for each of the chapters. It's super helpful. There's also some quick reference chapter reviews, and these are useful like when you're doing homework and such. But for the liquid solids and intermolecular forces piece, it would be worth going over, it has that chart that we just looked at, that summary chart. It also has properties affected by intermolecular forces. So this would be worth going over, like, because it talks about how viscosity is affected by intermolecular forces, how surface tension is affected by it, specific heat, boiling point, and vapor pressure. Each of these is an important topic, which we'll probably get to a little bit later on. There's also an extension where you'll see the Clausius-Clapeyron equation, or there's some mathematics that we're going to you'll end up doing a bit later. Depending on your professor, it may go deeper or less deep into it. But this will definitely be useful going forward. So I hope even if we weren't able to cover everything today, we're giving you some resources you can kind of take with you. And in fact, I'll even go ahead and copy and paste that review into the chat so that you can have the, download that and have that quick reference review. And like I said, feel free to check out our website. There's lots of great practice problems and answer keys, and lots of really good video tutorials as well. Liquid, solids, and intermolecular forces, questions, answer keys, including some more of the complicated calculation ones. So definitely feel free to check that out. We hope that will be helpful for you.
Thank you, Victoria and Jeffrey, for coming tonight. Hope it was helpful.
And feel free to send us feedback. I mean, you can email Dr. Neely at nilofar.askarian@tccd.edu or me at michael.depaul@tccd.edu if you have any questions, or honestly, even if you have just suggestions for improvement, because we're always looking to improve our sessions. Thanks, Jeffrey. We appreciate it.